Okay, this is our complex numbers. First of all, we're just going to do a very quick recap of all we've done from last in the first module, which was our AS1 module. So, if you've got your complex numbers, z is equal to x plus iy. X is a real part, I is the imaginary part. Okay, what we're going to look at here is our exponential form of a complex number. So the exponential is not very clear here, but it says z is equal to r e to the I theta. So that really is equivalent to just your z is equal to x plus iy can be written in the form z equals r e to the I theta. So that's where r is equal to modulus of z and theta is equal to the argument of z. So you could draw this out and find your argument of z, and then that's what your theta becomes. Okay, right. So if we skip down here, and where we get this from is if you do out your cos theta by Maclaurin's, you get cos theta is equal to 1 minus theta squared over 2 factorial theta to the power 4 over 4 factorial minus theta to the power 6 over 6 factorial and so on. Sine theta is equal to theta minus theta cubed over 3 factorial plus theta to the power 5 over 5 factorial minus theta to the power 7 over 7 factorial. So, your e to the x is equal to this. So e to the I theta, after a wee bit of working out, good bit of working out, works out to be this. So you can see e to the I theta is equivalent to, that's your cos theta plus I times your sine theta. So that's where it comes from. That's sort of proof of where that comes from. So you can see e to the I theta is equal to cos theta plus I sine theta. So that means if your z is equal to r times cos theta plus I sine theta, then is equivalent to r e to the I theta as well. Okay, right. There's another way of doing this as well, so I'm just going to put that in up here. So that was from Maclaurin's. Normally I don't do it that way, as normally we would have seen Maclaurin's later on, but just the order we did things this year, we have already seen Maclaurin's, so that's fine. So just to show you another way, this is normally the way I would show this. So I would just say let z, so can we add this in please, let z equal cos theta plus I sine theta. And then what we're actually going to do is we're going to do dz by d theta. So we're going to differentiate this thing with respect to theta. So if we do that, we will get minus theta plus I cos theta. And then we're just going to factorize out, it's a bit weird, we're going to factorize out an I. Okay, so I times, here you can see, I times cos theta would give you the I cos theta, so we're just going to write cos theta. And then I times what would give you minus sine theta. So it's actually going to be plus I sine theta, because remember, I squared equals minus 1, so that's what we have here. You have I times I, which is I squared, so I squared is minus 1 times sine theta, so minus sine theta. Pardon me, so what we have shown is that dz by d theta is equal to just I z. Okay, a wee bit of working out, you're going to have to squeeze this in here. So if we look at that again, then we can say, we've said dz by d theta is equal to I theta, and then what we're going to do is a wee bit of a lovely mathematics separating the variables. So I'm going to bring the z across, I'll have 1 over z dz, the integral of that is equal to the integral of I d theta. And if you integrate 1 over z, what you're going to get is ln of z. And if you integrate this, you're just going to get I theta. Oh, sorry, I theta plus c. So we'll just write that up here. That's ln of z equals I theta plus c. And we're going to put in what we know. So when theta equals 0, so looking back up here, when theta equals 0, when theta equals 0, you're going to have cos of 0 equals 1, sine of 0 equals 0. So when theta equals 0, z equals just 1. So when theta equals 0, z equals 1. Theta equals 0, z equals 1, which means 1 is equal to, so what that means, you've got, ln 1 I should say, ln of 1 is equal to just 0 plus your c. So c is equal to ln of 1, which is also equal to 0. So the story so far, we found out that ln of z is actually equal to I theta. And then if you inverse ln, the opposite of doing ln is doing e to the power of something. So z is equal to e to the power of theta. Okay, and it's just next rest of that is just a wee summary. So then you say z is equal to r times e to the I theta, where r is your modulus of z and theta is your argument of z. Okay, on to a few examples then. So first example, apologies for how fuzzy this is. We have 8 examples to do here, unfortunately, so a fair bit. Right, express the following in terms of, express the following in the form re to the I theta, where theta lies between minus pi and positive pi. So, very easy, the first one. You really can just write down, your r is clearly equal to root 2. Your theta is equal to pi over 10. So it really is as easy as just writing down z equals root 2 e to the pi over 10 times I. E to the pi over 10 times your I. Okay, part B. We tricked to it at the very start. And remember, it is z is equal to r times cos theta plus I sine theta. So we don't have that at the minute. So we've got to change that. That is 5 times cos of minus pi over 8 plus I sine of minus pi over 8. We're now good to go. So now clearly you can see your r is equal to just 5, and your theta is equal to minus pi over 8. The minus is important. So your z then is equal to 5 e to the minus pi over 8 times I. Okay, that's all well and good. These were already in modulus argument form, so ridiculously easy to change to your exponential form. Wee bit trickier than whenever it's not, but just it's basically the same as a question like in your AS1 module, when the question said write this in modulus argument form, this example. So we've got z is equal to 2 minus 3i. We've got to get it in the form r times e to the I theta. So we're going to have a 2, and we're going to have 3. So I'm just drawing my z, which is equal to 2 minus 3i here. And what we need to find is this angle in here. So it's nothing more than a bit of very basic trig. And also we're going to find the length of it, which is going to be your r. So we'll do this all here. Your r, just by Pythagoras, is going to be the square root of 2 squared plus 3 squared, which is going to be 4 plus 9, which is going to be 13. So root of 13. And your theta, tan, remember from your SOHCAHTOA, tan is opposite over adjacent. So tan is equal to 3 over 2. That means theta itself is tan to the minus 1 of 3 over 2, which means theta is equal to, and I have got minus, well, I would have done that, I got positive, but remember it's this way, so it's going to be a minus 1. It's below the real axis, I should say. So minus 0.983 to 3 sig figs. Okay, I haven't actually answered the question, so just answer the question. Just say, therefore, z is equal to root 13 e to the minus 0.983 times I. Okay, example 3. What we've done in this one, it says express, more of the same, just express z is equal to root 2, 3 pi I all over 4 in the form x plus I y. So very easy to do. What I would do here is convert it back to the form r times your cos theta, which was 3 pi over 4 plus I times your sine of 3 pi over 4, which means z is equal to root 2, and if you do cos of 3 pi over 4, this really is just a calculator exercise. Bang that into your calculator, see what you get. And fill that into your calculator, you got minus 1 over root 2 plus I times 1 over root 2, and then multiply out. Very easy, that's going to be minus 1 plus I. Okay, example 4. Example 4, same idea. You've got to express it in the form r cos theta plus I sine theta. So very easy this one. You're just writing it as 2 times cos of 23 pi over 5 plus I sine of 23 pi over 5. And now just have a wee look at the trick in this question. They've said that this is between minus pi and positive pi. So ours are clearly not within that range. So let's just at the side look at our 23 pi over 5. So think about what that is. That is 4 complete lots of pi plus 3/5 of a pi. So let's just take away 4 pi from it, and you're left with 3 pi over 5. So it's 2 full terms plus another 3 pi, which is equivalent of just 3 pi over 5. So when you do that out, that just becomes, it really is just the same as 2 upon cos of 3 pi over 5 plus I sine of 3 pi over 5. Okay, this question is a wee bit different and leads to something we'll be seeing a bit later on. It says use e to the I theta equals cos theta plus I sine theta to show that cos theta equals a half upon e to the I theta plus e to the minus I theta. Now there's a wee clue in this. They've mentioned, you already know what e to the I theta is, but in their answer they've got e to the minus I theta, so you want to think about that. So we'll just write down e to the I theta first of all. E to the I theta was equal to cos theta plus I sine theta. So if you do e to the minus I theta, and I'll show you a bit of working out to do this, that's going to be cos of minus theta plus I sine of minus theta. So a bit similar to the example we had up above. If you do cos of minus theta, it is exactly the same as just cos of theta. Why that is, that's just from your cast diagram. There's your 0. So for example, cos of 30 is the same as cos of minus 30. So that's exactly why. That's why. Okay. However, sine of minus theta would be the same as minus theta times sine theta. And again, go to our cast diagram. Should have left that up. Go to our cast diagram. Cos is positive here, so you have, sine is positive here, but sine is negative here. So like sine of theta would be the same as minus of sine of minus theta. Okay, so here, that's what you've got for your e to the I theta and also your e to the minus I theta. Now if we just add those two things, we just add e to the I theta plus e to the minus I theta, what you will get is 2 cos theta. Therefore, your cos theta will be equal to a half upon e to the I theta plus e to the minus I theta. And that is that bit done. Right, just while we're on this one, we'll look at what it would be, how you would get what sine theta is. So we're going to do that. If we got the cost one by adding your e to the I theta and e to the minus I theta, what we're going to do this time is subtract. So do e to the I theta minus e to the minus I theta, and then what would you get? So if you do that out, what you're going to get is 2i sine theta, and therefore a wee bit of working out, you're going to get I times sine theta is equal to a half upon e to the I theta minus e to the minus I theta. I wouldn't divide across by this I would just leave it, make I sine theta the subject, so it's just don't be writing it as I is equal to, or sorry, don't be writing it as sine is equal to, just leave it as I sine theta equals, that's a nice way to leave it. Okay, way on down the road, we'll be using that when we're looking at DeMoirves theorem and finding values for, or expressions, I suppose, for cos theta, cos 6 theta, maybe like cos to the power 5 theta, and so on. So these things will come into play an awful lot more later down the road. Okay, multiplying and dividing by complex numbers. Right. Basically, if you have two complex numbers, you can multiply their modulus, and two complex numbers, z1 and z2, and if you multiply them, then the modulus of z1 times the modulus of z1 times z2 is just equal to the modulus of z1 times the modulus of z2. So it's really, really easy. So if you have them in modulus argument form, or if you have them in exponential form where you've got the modulus and an e to the argument basically, all you do is you multiply the modulus. Really easy. The arguments then, for the arguments, the argument of the product of z1 and z2 is just equal to the argument of z1 plus the argument of z2. Likewise, if you divide z1 and z2, the modulus of z1 divided by 2 is the modulus of z1 divided by the modulus of z2, and the argument of z1 divided by z2 is the argument of z1 minus the argument of z2. Okay, so if you apply these to what we've just done, modulus argument form, z1 times z2 is equal to modulus of r1 modulus of r2, then e to the power of I theta 1 plus theta 2, and that's where theta 1 and theta 2 are the arguments. Likewise, z1 divided by z2 is modulus of r1 divided by modulus of r2. Z1 divided by z2 is r1 divided by r2, and the argument is theta 1 minus theta 2. Okay, so nice easy example here. So example 7 says express 2 cos of pi over 12 plus I sine pi over 12 all divided by root 2 cos of 5 pi over 6 plus I sine 5 pi over 6 in the form r e to the I theta. Okay, first thing I'm going to do is write the top line in the form r e to the I theta, so that's 2 e to the I pi over 6, and the bottom line, the denominator, is root 2 e to the I 5 pi over 6. So if you do that out, you're just going to divide the moduluses. You'll have root 2 over root 2, and then subtract the arguments. So I'm going to show a bit of working out here. That's e to the power of I times, that should be a pi over 12 up top there. Let me change that, please. E to the pi over 12 minus 5 pi over 6. Bit of a mess here, but if we go across, 2 divided by root 2 is very nice, it's just root 2, and then if you just do that on your calculator, you're going to get minus 3 pi over 4i, and that is it. Okay, our last thing here in this bit of notes is on DeMoirves theorem. So, Euler's relationship, which was our e to the I theta, or our exponential form, we have r cos theta plus I sin theta is the same, r cos theta plus I sin theta by Euler's is the same as r e to the I theta. Now what we're going to do here is we're going to square that. Now if you square it, it is just, remember, that would be r cos theta plus I sine theta upon r sine theta plus r sine cos theta plus I sine theta. So basically you just multiply the moduluses and you add the arguments. So if you, by the logic from what we've just done, that would then just become r squared, and it would become cos 2 theta plus I sine 2 theta. Likewise, if you cubed it, if you did r cos theta plus I sine theta all cubed, that would be r cos theta plus I sine theta upon r cos theta plus I sine theta upon r cos theta plus I sine theta. So you would have your modulus, just multiply r times r times r, which becomes r cubed, and your arguments add, so theta plus theta, which is 3 theta, and so on. So in general, the result that we get is this. So can we highlight this in some way, shape, or form? For any integer, r cos theta plus I sine theta all to the power of n is just your n, your modulus to the power of your r is your modulus, and it's raised to the power of n, and your argument is multiplied by n. Okay, Euler's relationship can actually, DeMoirves theorem, sorry, can be quickly proved using Euler's relationship and also induction. So we're not going through this in much detail, but you just see for induction, the idea of induction is usually prove something true for a value, say 1. So you find it's true there, you assume it's true for a value n is equal to k, and then you prove it's true for a value n equals k plus 1. So then that means if you've proved it true for n equals 1, and you've proved, and you know you've assumed it's true for n equals k, and then you've proved it true for n equals k plus 1, then it's true for all values 1, 2, 3, 4, and so on. Okay, so that's the idea behind our induction. You'll see that. We have seen that already, our induction. So you're basically proving it true for n equals 1. You've got your left hand side is equal to this, and the right hand side is equal to this, so you can see it is true for n equals 1. If you're assuming it's true for some value k, i.e. you're assuming that r of cos theta plus I sine theta to the power of k is equal to r to the power of k cos the k theta plus I sine theta. And then if by induction what we want to do is prove it true for n is equal to k plus 1. So r of cos theta plus I sine theta to the power of k times r of cos theta plus I sine theta, that's what r cos theta plus I sine theta to the power of k plus 1 would be. When you multiply it out, what you get, and you can see the working out here, so pause that if you want to watch that again, but it's just r to the power of k plus 1 upon cos of k plus 1 theta plus I k plus 1 times theta. So you can see it's true for k, n equals k plus 1. Alright. And then you can see the last wee step 4 is just proving that it's true, showing it is true. Okay, example 8, last example for us today in this video. So here, what we're going to do for example 8, we're going to simplify this expression. So we're going to use DeMoirves theorem to do this. So just equals, and we've no r's involved here. Well, we do have an r, but the r's really are just 1, so we don't have to worry about them. Just get rid of those. So all we have to do is multiply this to the power of 5. It means you're going to multiply in by your 5, so your arguments get multiplied by 5. So it's going to be cos, and it's going to be, I'll show my steps, 5 times 9 pi over 17 plus I sine of 5 times 9 pi over 17, and your bottom line is going to be cos of 3 times 2 pi over 17 plus I times sine of 3 times 2 pi over 17. So again, just write that out. That's going to be cos of 45 pi over 17 plus I sine of 45 pi over 17. And then bottom line, multiply it out, it's going to be just 6 pi over 17 plus I sine of 6 pi over 17. And we'll go up here to finish this off. Apologies. Now what we have then, we just have a complex number divided by a complex number. They're in modulus argument form, so we can just subtract the arguments, just like we did in AS1. So it's going to be really cos of brackets 45 pi over 17 minus 6 pi over 17 plus I sine of 45 pi over 17 minus 6 pi over 17. And if you do that out, what you will get is cos of 51. Oh, I have made a mistake.
The bottom line is negative, so should your angle be negative?
It should indeed, absolutely right. Yep. The cos bit doesn't need to flip. We'll just leave it as it is. But well, no, sorry. The cos bit strictly does need to flip as well. It's going to be minus 2 pi. Apologies, add that wee minus in there, folks. So that's me minus and minus, and then that becomes 45 pi over 17 minus 6 pi over 17 becomes plus. There we go. You can see with at least I have set my work out well, so it's easy to fix. And then plus, and then that's my sine times 51 pi over 17, and then that works out to be cos of 3 pi plus I sine of 3 pi. And once you get to here, folks, I would just fire that into the calculator. Cos of 3 pi is going to be minus 1, and sine of 3 pi is going to be 0, so it actually just works out to be minus 1. Okay, just to see the mistake that I'd made there, you can see I hadn't originally, when I did this, I'd missed this out. So just be careful, remember it must be in the form of cos theta plus I sine theta, which we had, and we had a minus here. So there was a trap on this question I completely fell into it. So here it was cos of 2 pi over 17 minus I sine of 2 pi over 17. I really should have written that as cos of minus 2 pi over 17 plus I sine 2 pi over 7 plus I sine of minus 2 pi over 17. Don't change this bit. Leave this bit as it is. We know we can write this really as cos of 2 pi over 17, but that doesn't help us here, because here we want to know what the actual argument is, and the actual argument is minus 2 pi over 17. So you need to have it in that form in the question. Okay. Right, that is our notes done for this bit.